fast. So yeah, let me first thank KITP for providing the framework for this program and also the conference. In fact, maybe at this point I should point out this picture, which may not be the most beautiful picture of KITP. I took half an hour ago on my way to this conference. And so I think this is a fantastic place to be, obviously. Let me also thank the organizers for putting together this meeting. In fact, twice, and I think now it's really the perfect time to meet after we escaped the long lockdowns. And so I'm excited to be here for the next month or so to work on problems of integrability. Now, before I forget, I wanted to point out that the work I'm going to report about is work in collaboration with quite a few, mostly younger collaborators. There's a first group, Misha Isachenkov, Ilya Buric, Petro Liendo, Yannick Linke, and Evgeny Zopko, with whom I did work that was actually ready by the time of the original meeting in 2020. And then another group involving also Ilya Buric and then Sylvain Lacroix, who is now a postdoc at ETH, Jerry Mann, who is going to be a postdoc in London, King's College, Lorenzo Quintavalle, who is going to Canada as a postdoc, and I forgot one, Ilya Buric, who is in Pisa as a postdoc. So that's actually work that was done in the last 2 years while we were waiting for this event to happen. And so I'll report about that here as well. So this talk is about conformal symmetry. And of course, I think everybody in this audience is very well aware of what conformal symmetry is and how important it is. In fact, it is now sort of understood since about 50 years how relevant and powerful conformal symmetry is. This was the early work of Mak and Salam, and then Ferrara, Gritto, Gallo, Todorov, Dobrev, and Polyakov in particular, so around the 1970, which first understood it as a consistent symmetry to impose in quantum field theory, and then also the constraining power. Now, the subject, of course, as you know, went in the 80s mostly into two-dimensional conformal symmetry. A lot of work was done. But then I would say at least for 25 years ago with ADS-CFT, we really also understood how important it is to think about conformal field theory in higher dimensions, if we weren't convinced before. Now, I think since then, most people of our community, much beyond this, are actually working in some way or another on conformal field theory. So it's a very relevant topic. But then when you look at the methods that we are using to actually deal with the actual symmetry that we think is making all this difference, this is pretty much the methodology that was developed and applied by Wigner and his contemporaries in the early days of quantum mechanics. And so one of the key messages of this, so the fact that we are using such old-fashioned methods kind of hampers progress in the field. And I want to make that point and illustrate that point in a moment. But before I do so, let me say the key message of this talk is that this doesn't have to be. There is actually, at the beginning of the 21st century, beautiful, powerful technology around. And good for this community here, people in this room, it's really the mythology of integrable systems that can really make a difference. And so my vision is that maybe sort of the report from this program will kind of contain a blueprint for kind of this modern treatment of conformal symmetry that should be developed now that the tools are there. Now, in the last I made a few statements that maybe seem a little exaggerated, and so I've tried to kind of make that a little more precise. So what is the challenge of conformal symmetry, and why am I saying that we have not really addressed or solved these challenges? So in this talk, I will kind of think about conformal symmetry for arbitrary objects or correlation functions that you might want to consider. So the standard thing is, of course, you do like correlation functions with a bunch of local fields. But of course, many people here also think about other things. You can put like Wilson lines or other defects in your theory. You can maybe even have little defect operators on these Wilson lines. All these things are objects that we study, for instance, to explore N equal 4 super Young-Mills and explore the dynamics of that theory or other theories. So this is sort of the basic objects. These are correlation functions, could be of local fields only or including some defects, Wilson line surface operators, and so on and so forth. Now, the power of conformal symmetry allows us to kind of, when you get these functions, of course, like a 4-point function of local fields is a very complicated thing, right? I mean, it has a very complicated dependence on the axis, on the coordinates insertion points of the fields. But so what we've learned already in the early 70s is that what we should do is we should do these conformal partial wave expansion. We should expand these quantities in a beautiful basis of functions, very much like plane waves and translationally symmetric theories. And then when we do that, then we kind of can put all the dependence on space-time into some kinematically determined function known as conformal blocks with coefficients which are constants, and they contain all the dynamics. So that these conformal partial wave expansion, these kind of Fourier decompositions with respect to the conformal symmetry, these are sort of the most powerful analytical tool that we have. It allows a very neat separation between the kinematical skeleton of a theory. Again, this is completely kinematical, these objects here. So it should be determined by symmetry, these functions, and the dynamical coefficients, which are really just numbers. And moreover, the power of conformal symmetry is that implies that these coefficients actually factorize in a beautiful way. You know that from a 4-point function, for instance, it factorizes into a product of 3-point couplings. So these coefficients have a very nice coupling factorization properties, and that I call sort of the dynamical Lego. So these coefficients that contain all the dynamical information, they kind of, you just need a few of them, and then you can build everything that you want in your theory. Now, so that's sort of the symmetry input. So the symmetry, conformal symmetry, should tell us what these functions are. These are functions of the cross ratios of your configuration. Now, let me point out one thing, maybe that seems a little technical. So this is, of course, in some sense, a basis of functions. So you have some quantum numbers, capital lambda here. And in order to have a real basis, there should be as many quantum numbers here as there are variables. So like you have as many components of momentum when you make a Fourier decomposition as you have coordinates. And so we will get back to that later on. Now, once you have these, I mean, assuming that you have these conformal blocks, you know what these look like, then you can, for instance, take your favorite result of a computation. For instance, you computed, like, say, a 6-point function of local operators at n equals 4 superior nulls, and you can then decompose them into these blocks and harvest sort of dynamical information. Of course, these blocks are also fundamental for the Bootstrap program, which I will not talk about so much today. Now, what's really, why am I claiming that we are far behind kind of addressing this challenge? And so the issue somehow why we haven't really like aren't able to fully leverage the power of conformal symmetry is an issue that we know very well. It's somehow we have very good tools to write down. So I mean, these conformal blocks, these function g that I had sort of this lowercase g here, these actually we can write as integrals, and we have very good rules to write the integrands. But we do not really know what the integrals are. So this is something that we're, of course, very familiar with, like from for instance, Feynman integrals, right? We have very nice tools to write down the integrand, but then when it comes to actually integrating, then, of course, then we are challenged, right, up to this very day. And so this is the same type of challenge that I'm saying conformal symmetry poses. And that has not been really fully resolved, not been resolved. So let me recall, if you have a 3-point function in the conformal field theory of 3 scalar fields, you all probably know that this is completely determined up to one coupling constant by conformal symmetry. You get this typical 3-point function. I'll use a symbolic notation for that. There's the coupling constant and then this free vertex. And I have a single line here because I have 3 scalar fields. Scalar fields have a single quantum number, just the conformal weight. Then you can also write down a 3-point function of 2 scalar fields and one field carries spin. So let's say spin is a symmetric traceless tensor representation. That's one extra quantum number. So I write here this symbol for it. So it has one leg with 2 lines because there's 2 quantum numbers, spin and weight, for that field. And so I here give you only the symbolic notation. You can also write a complete function, but I mean, I don't really want to go through the thing, introducing all this notation for this. So there's a concrete function similar to this function that corresponds to this 3 vertex. And all these things, of course, are already contained in this classical book reference for conformal group theory from the 70s by Dobrev and collaborators. But now when we want to build the conformal block, what we do actually is we take, let's say, two of these words. So we have four scalar external fields. And then, in the operator product expansion of two scalar fields, you can actually create fields with spin, right? Because, and so you take two of these vertices of this type and put them together and then integrate kind of over intermediate states. And that way you get so this Z here is an integration roughly that has to do over polarizations for the spin degrees of freedom. So I didn't really talk about that too much, but it's just meant to be as a formula. So you get these things here. These are concrete functions which are well known. And then you put them here and then you integrate over these intermediate states and you get an integral. I carried out here the integration over this Z. And so the types of integral that you get is of this type. And that's roughly of the complexity of computing sort of Feynman integrals, right? I mean, in fact, you can, so this is a complicated integral. When you look at that, I mean, this is not obvious what object it actually defines. It will be a function of, the function of the cross ratios somehow. But it will depend somehow on this deltas, so external deltas and L's, internal deltas and L's. But what is this object? So in fact, in the 70s, when people asked that question, they just didn't know the answer. And I think that's why there was so little progress. I mean, one of the reasons why there was little progress in the 70s on a higher dimensional conformal field theory in terms of really solving the word solution. And it was only in the beginning of sort of around 2000 that Dolan Osborne thought of a strategy of taking these integrals and characterizing them through differential equations that they satisfy. It's also a technique that is very well used in Feynman integration. So they wrote down differential equations and studied these differential equations, and they made progress, at least for 4-point functional scalar fields, made progress in answering what these objects are. And it turns out that they're some sort of hypergeometric functions. And that really paved the way for all this recent progress from 2010 on the modern bootstrap. So, but this is work mostly focused on the 4-point function of local fields. And as I said, the scope that I have here is much broader. I mean, we have lots of these challenges. The 4-point function of local fields is by far not the only object quantity that we're discussing. And so, so what I'm trying to make today, the point is that there is a solution, and the solution is integrability to this problem. So it turns out that these differential operators that you use to characterize conformal blocks, not just conformal blocks of scalar 4-point function, but all conformal blocks, these turn out to be Hamiltonians of some interesting integrable system. Okay, and the purpose of this talk is to show you these integrable systems and tell you a little bit what's known about them. So this brings me to the plan of this talk. I will actually have two parts. I will first, in part one, kind of, let's say it's a bottom-up approach. I will, this will not be completely generic. Deal with a bunch of setups, for instance, scalar 4-point functions, or if you have a Wilson line and two scalar operators in the bulk, or two Wilson lines. These type of blocks that you need for such configurations will be treated in this first part. And it will give us a very good idea of what kind of integrable models appears. And then in the second part, so that's the part that was basically developed since 2020, since our original plan to meet. I will develop or describe a top-down approach, which will kind of locate these integrable systems within the landscape of Godin models. But it's very important, and I pointed out right away, is that these are not Godin models in general, but they have special limits of Godin model, and that is a very important fact. So you kind of might overread these limits of Godin integral models. So the message is limits, and these have very particular properties. And then I will conclude with some statements and a long list of open problems that I hope to address with you in the next week and month. Okay, any questions on the introduction?
So this is
Yep. This is quantum integrable systems, right? We're discussing, so the claim is the conformal blocks are really quantum wave functions of an integrable system. And
differential equation.
So the differential equations are the Hamiltonians. I mean, these are differential operators. These are quantum Hamiltonians for the system. Yep. Yeah, thanks for the. Okay. So yeah, I invite questions as I as I go, of course, right, we have the separation, but we have to use up at least 20 minutes, as we know. That's the rule, 20 minutes of question time. So we have the talent. Okay, good. So let's do the first start with the first part. So I want to give you an idea of the type of integrable systems that appear in a somewhat restricted context, which I call Casimir-solvable cases for reasons that I may be able to explain as we proceed. So I should say that as this dates from pre-pandemic, some of you probably have seen this discussion before, and so I made it a little more different from what I usually discuss. So normally at this point I will discuss sort of the integrable system attached to a 4-point function of local fields, just to give some variation to those of you who have seen this before. I'll now discuss the integrable system attached to like a defect and 2 local fields. The discussion is very similar. So you can think of, you have a Wilson line, you put 2 local fields and you want to know what the blocks are in which you expand such a configuration. And so I should tell you also, maybe because that's familiar, so this setup also has 2 cross ratios. So like a 4-point function in conformal field theory, we have 2 cross ratios. Also, if you have 1 defect, no matter what dimension the defect has, what dimension you're in, and you have 2 local fields, then you have 2 cross ratios, and you can kind of easily play with your conformal frames to see. So 3 points of, I mean, basically yeah, maybe we'll. Okay. So if you want to know the reasoning, ask a question that counts towards question time. Okay, so I want to show you the kind of integrable system and how you obtain the integrable system, describing sort of characterizing the conformal blocks for this setup. And so the first thing that I'm doing is a very basic elementary fact. So you all, I think, have seen that when you have primary fields in the conformal field theory, they're characterized by sort of transformation behavior with respect to conformal generators. And here I wrote the transformation behavior with respect to dilations. So that's for a primary field of weight delta. Now we can actually build objects that have this transformation behavior from functions on the conformal group. So imagine you take a function on the conformal group. So in particular, it's a function that you can evaluate on the exponentials of the translation operator. These are particular elements of the conformal group. And now imagine that you apply sort of a dilation, like a right infinitesimal left transformation dilation to this object. Then what you can do is you can actually move, you're using Baker-Campbell-Hausdorff formula, you can move this dilation through the translation. Using the standard commutation relation conformal group, you get this expression. And then, of course, you have here the momentum, so you can write that as a derivative with respect to this x coordinate. And now if we assume that this function f has a covariance property with respect to d that allows us to take d when it's on the right side out with an eigenvalue minus I delta, so it has particular covariance properties with respect to infinitesimal left transformation, then we get indeed this transformation behavior. So that's saying that we can actually construct objects that have a transformation behavior of a local field, local primary field, from functions on the group. So what we take is we take functions, arbitrary functions on the group, let's say complex valued, and we demand that when we do right transformations with respect to, let's say, rotations, dilations, that it transforms in some particular way. So let's say for scalar field, the transformation behavior under rotations is trivial, under dilations is as described here. And the transformation behavior under special conformal transformations would also be trivial. So functions of this property, they will actually transform in the same way as a primary field. Okay? So another way of saying that, so I introduced here a few symbols. So the conformal group, the Euclidean conformal group is SO1, D plus 1. This group K that I used here, K was element in K, was a product of dilations and rotations, and N is the special conformal transformations. So these functions here, because of these covariance properties, are essentially functions on the quotient of the conformal group divided by special conformal transformations and rotations. But that's basically what's left is translation, so that's RD. So you get functions of D variables, and these functions of D variables behave the same way as as primary fields. So that's a way to construct explicitly differential operators. So you can act now with the left transformations, as I did here, and compute all the transformation operators. This is first order differential operators to describe the behavior of primary fields. Okay, so that's a known construction of what is called continuous series representations, or any kind of representations of the conformal group. So you can actually, just as and this is an aside, you can do the same when you're dealing with defects. So in that case, so we have conformal generators acting on a local field. That's what I described here. But we also have conformal symmetries acting on an operator that inserts a Wilson line, for instance. And the way you kind of find the differential operators is the same technology. You notice that the defect or p-dimensional defect preserves the symmetry, which is conformal transformations along the defect, SO1, p plus 1, and then rotations in the transverse direction. And then you do the same thing. You take functions which are invariant under right transformations with respect to the subgroup, and then act from the left with your conformal generators, and you will get a bunch of differential operators to describe the action of the conformal symmetry on this defect operator. So it's different formulas from what you use for local primary fields, but it's the same type of derivation. Okay, so this is kind of just mathematical background that I want you to have. There's one more statement that comes actually from this classic book of Dobrev and collaborators. So we are now gearing towards understanding invariance in the tensor product of representation. So we say two primary fields, both are attached with a certain subspace of function on the conformal group, and then maybe one defect, another space of functions on the group. And we're looking for a conformal invariant there. So in particular, since we have two defects, we have to two local operators, we have to understand what the tensor product is of these two representations that come from the primary field. So this is a group theoretic terminology, what it means to take an OPE. And so it turns out, and that's a statement that you can just find out also the proof in this book, if you take a tensor product of these two representations that correspond to a primary field, you can actually also model that through functions on the conformal group. And these times it's functions on the conformal group which only have convariance property with respect to K, this group of rotations and dilations, but not with respect to special conformal transformations, and of this form. So this, of course, are functions basically on G mod K. G mod K contains, so K contains dilations and rotations, so it doesn't contain special conformal transformations and translations. So G mod K is roughly a 2D dimensional space, and that's what you expect for describing fields localized, or two fields localized at points. So, so now we can actually, using this statement from this old book, we can actually address our main topic. So we take now the primary field, represented here by this space of functions on the conformal group, another primary field with weight delta 2, this space, and then a defect, which is another space of function on the conformal group. And we take the conformal invariance with respect to that. So then we use this statement up here. We replace this tensor product of these representations by this space of functions on G mod K, or K covariant functions on G, times this. And then we take G invariance, and it turns now out, so you can think of these as functions which are K right invariant, and these are functions which are KP or GP left invariant. GP was the group that keeps the defect invariant. And so when you divide by G, you essentially get functions which have both left and right covariance properties. Under action from the left with K, they transform according to the transformation behavior, I mean, that encodes the weights of the fields. And according from when you multiply with elements gamma from the defect conformal group, they should be invariant. And so this you can think of as functions on the quotient, on the double quotient, where you take the conformal group, and on one side you divide by K, and on the other side, so that's a 2D dimensional space, and then you divide also by GP. And that's a space which you can check is actually 2-dimensional, this quotient. Okay, so you get a 2-dimensional space here. So you get in some sense functions of two variables, and these are the two cross ratios. So what we have done now is we have basically located in the space of functions on the group where our conformal blocks, where our conformal invariants sit. Okay, there are particular functions which have these covariance properties. And now the next step is, so the step to integrability is now super small. Imagine you write down your Laplacian on the conformal group. So Laplacian is invariant on the left and right transformations. So it has to descend to this double quotient, right? So like one example that you can easily do is, I mean, you'd write down the Laplacian on the free sphere, SU2, right? You all remember this expression in terms of Euler angles. And then you descend to the double quotient, which means you take the derivatives with respect to two of the Euler angles and replace them by constants. These constants are essentially the anomalous dimensions. So you will get a differential operator, second order differential operator in one variable, because two of the variables you have, I mean, derivative with respect to two variables you have replaced by a constant. And so that's a second order differential operator that you can work out. So that was for SU2, for rank 1 case. Now, fortunately, Harishandra has done this calculation, and many others has done this calculation for us for all the higher rank cases. And they figured out that whatever you do in this setup that I just described, when you kind of take this Laplacian of the conformal group and now descend down to this double quotient by imposing these covariance laws, then you will end up with an operator. Okay, it's a differential operator, a second order differential operator if you start with the quadratic Casimir in two variables, because there's two cross ratios left. The quotient has two variables, unlike in this example of SU2 where it was only one. And after a minor modification, you can actually bring this into a form of a quantum mechanical Hamiltonian. Okay, so which I wrote here. I mean, again, you don't need to look at the details. What this is basically a standard kinetic term with respect to two variables, which are related somehow to the cross ratios of this configuration. Details are not so important. And the potential. And this potential contains, so it's basically lots of Sinch divergences. So you can think of it as sort of describing sort of two particles moving in a potential. That's kind of a semi-infinite potential. So this is the potential they're moving in, and then they also interact with this interaction term. Okay, so the standard has the form. So the Laplacian, and again, I invite you to do this for this SU2 example because it's really nice to see. In that case, you get just Peuchet-Teller Hamiltonian. In this case, you get this beautiful Hamiltonian. Well, maybe beautiful for me after working with it for so long, but maybe also for many of you. So that's a so-called, has the form of a Calogero-Sutherland or Calogero-Musa-Sutherland Hamiltonian of hyperbolic or trigonometric type. Now, these coupling constants that appear here in front of these various terms, they are just determined by your setup. So for instance, in the coupling constants, you have the dimension of D of your conformal field theory, the dimension of the defect that you put, so the P would be 1 if you have a line defect, and the dimensions, the conformal weights of the two local fields that you put. Okay, so whenever you dial your configuration, your weights, your dimensions, you fix these constants, and then you get typically some kind of interacting two-particle quantum mechanics system that describes your setup. Now, this Hamiltonian. So for 4-point function of local fields, it's very similar to this. You have a different choice of coupling constants and slightly different boundary conditions, but it's a similar setup. Now, so this was our first pass to integrate. So I didn't say much about this because I guess most people in this audience know when they see this Hamiltonian that it's integrable. In fact, these type of Hamiltonians were written down for the first time in the 70s by, as I said, Calogero, Moser, Sutherland, as some sort of solvable, integrable analogs of this famous Peuchet-Teller problem that was already solved in 1933 by Peuchet-Teller. And so then people went ahead and think, what can I do if I put several particles in this Peuchet-Teller type potential and make them interact? How can I make the interaction so that this problem stays integrable, in fact, even super integrable? So there's even Runge length vectors for these problems. And they came up with this type of Hamiltonians, which have some beautiful structure that I will not really talk about. And so then it was discovered by, as I said, by others in particular, Perlomov and Olshanetsky, that when you do this type of group theory problems, like take the Laplacian and descend to these type of cosets, that's usually what you end up with. And what I've told you before was basically these little exercises that we did, is that this is a problem that really appears in conformal field theory. And that's why, so there's 3 slides, we understood that sort of integrable Hamiltonians of Calogero-Sutherland type are appearing supernaturally in conformal field theory. And these are provide the differential operators we need to solve, or differential equations we need to solve if we want to construct conformal blocks. And in fact, I mentioned before that Dolan Osborne wrote down some differential operators for the scalar 4-point function. These differential operators did not have this simple form. They looked quite complicated, but you can actually take this expression in hindsight and just map them onto Calogero-Sutherland form. And if you had done that when Dolan Osborne wrote them down, you would have had the entire solution theory on the spot without like 10 years of extra work. So I will not talk here about the solution. So this is actually, upside is that this is a solvable system. A lot of things is known about the wave functions. If you want to ask me about this, that's would count towards question time. I'm happy to talk at length about it.
Can I ask a question?
Yeah.
So the appearance of the integrable model here, do you say that it's something expected from purely CFT perspective, or is it just that you compute it and it just happens to be? I mean, as I said,
it's expected when you know the work of Harish Shankar, for instance, then yeah, then it's completely expected. But it was not expected, right? I mean, so when people looked at this problem, I mean, they understood, of course, in the early 2000s there was a problem. We didn't know what these blocks are. They looked at it. Dolan Osborne wrote down their differential operators, and then they spent about 10 years developing sort of the math of that. And if they had suspected that it was an integrable problem, I think they would have just turned to the relevant literature and wrote down the solution, copied the solution from the books. Because so this treatment essentially, I'm happy to talk more about, this is mostly work in mathematics by Heckman and Opdam, where this was solved like in the early 80s. And so everything, if you look at the Dolan Osborne work, you can map one-to-one all their formulas to work that has been. But I think it was, yeah, I mean, I don't know, it depends on your point of view. It was not expected, so we actually, yeah, came across that in a very indirect way.
Just to continue on, I mean, integrability, I always think of associated with an infinite number of conserved currents.
This is quantum mechanical integrability, so we have finite EMA. So this is quantum mechanical integrability, right? This is a quantum mechanical system, not a quantum field theory system. Okay. So here integrability just means
you can have quantum systems in 1 + 1 with infinite number of.
Oh yeah. So again, I'm not talking about. So there's of course a lot of work on 2-dimensional conformal symmetry, and then of course you have integrable systems also with like infinitely many conserved charges. That's a different topic. Now we're discussing conformal symmetry for higher dimensional conformal symmetry. So where it's typically finite dimensional symmetry. Right, and the integrable systems that are associated with finite dimensional symmetry.
But are there secretly more symmetries because you have an integrable Hamiltonian or not?
You mean in a dynamical theory which is integrable? Yeah. Again, I'm talking exclusively about the kinematics.
Yeah.
Right. So, right. And there might be dynamical dynamical quantum field theories which are also integrable dynamically. I mean, we know that n = 4 is such an example.
But in general,
it's not. Like probably the 3D Ising model is not of this type, and this also applies to 3D Ising model, and not just the n = 4. Whether there's an interesting interplay between these integrabilities in some sense.
How do you know 3D Ising isn't?
I don't know, but I mean, maybe it is. Of course, secretly, of course, I hope it is. Yeah. But I mean, we have very little indications for that, I think. But yeah, it could be. But I mean, probably not every conformal field theory is integrable in the sense of having infinitely many commuting operators. And how these would kind of interact with these commuting objects that come from these quantum mechanics problems, kinematical problems. Again, one is in some sense, integrability that you mentioned is sort of a much deeper statement. It's dynamical integrability, whereas this is sort of, we're dealing really with pure group theory in some sense, but we address the fact that it's actually, there's a modern treatment of group theory that has to become, so it's not a trivial.
Can I ask you something?
Yeah. So Titina took case, so I know Alessandro, and then I don't know the order.
No, but just because it's connected. Since the beginning of your talk, actually looking at your paper, and the Lance and they preceded me because it's a connected question. Maybe it's a little bit silly at this stage, but So concretely, okay, this is cinematics, whatever you said, very beautiful, and finite number of conserved quantities. But what is the meaning of the conserved charges in the finite? Okay,
in
integrable system for
okay.
the higher dimensional conformal system.
Thank you for answer. So, what do these conserved charges? What do they actually measure? So they measure, in this particular case, they measure just the dimensions and spins of the intermediate fields that are exchanged in the intermediate channel. So if you have a 4-point function, I guess I should write it on this side because on that side I cannot read, but at least you asking the question. So if you have a 4-point function of scalar fields, then you know there is some field of weight delta and spin L exchanged, and these conserved charges measure these two quantum numbers. Okay, yeah, so this is actually, thanks for the question.
Yeah, that was my question.
Okay. Okay. Alessandro. Oh.
If you can comment a bit more. If you can comment. Okay. If you can comment a bit more on why do you get metabolic functions and whether there is some sense of it, maybe like the rational caloric.
Yeah, I mean, I can comment on this, and I mean, maybe I do these comments at the end because we will also see elliptic at some point, and then maybe when we have this, I make some comments about that, but probably towards the end, not to get this. But yeah, there is some kind of way to understand why it should be hyperbolic in this case. And other problems that we'll see, they will be elliptic. Yeah.
Sort of related, just, I noticed tau 2 is imaginary. Is this model real?
So now it depends, of course, also a little bit on what kind of, I mean, I did Euclidean conformal group. So the domain here, yeah, so I mean, it addresses, maybe then these questions also go together and I answer them right away. So you see, as you see that one of these parameters, tau 2 here, is chosen to be imaginary, the other one is real. So that means in one direction, this model actually is trigonometric, and the other one is hyperbolic. And I told you before, and the answer to the question before was that these operators measure weight and spin of the fields. Now, weight is, of course, a real quantum number, and spin is a discrete quantum number. So somehow we would expect that there is a sort of a compact direction, the trigonometric direction, where the particle is confined in a box, and one that is a scattering direction, where you have a continuum of eigenvalues. So I think that may be kind of this group of questions. Yeah, that's good to answer together. Okay. Okay, so that was, yeah. Okay, good. So, yeah, as I said, I mean, there's would be a lot to say here about the solution theory of this thing. You can ask me about this. I know, of course, Titina has asked me a few times before. I remember one time in Cages, like a few years ago, and then I had to really escape, and I never got to answer. So today you get another chance. And this time I cannot escape because I'm here for the next month. All right, but this is not the topic that I wanted to address in the second part of the talk. So back in 5 minutes left, but I mean, you have to add to discussion time, right? I mean, I counted 10 minutes discussion already. Okay, but yeah, I'll do my best. So back in 2020, while I was kind of, so I noticed, okay, the discussion I just gave was very well suited to discuss, for instance, 4-point function of local fields or 2-point function in presence of a defect, things like that. And but then when I talked to my CFT friends working on N=4 super mills or things like that, I realized, of course, they're often computing different observables, not just 4-point function. In fact, in N=4 super mills, I mean, there's a lot of stuff when you do like much higher point correlation function at some point, or like Wilson, Cast-Wilson loops and things like that, usually with a lot more points inserted. And so I was starting to wonder whether this story that I just described, and the conformal blocks, so clearly there's also sort of conformal blocks that would allow you to decompose such higher point correlation functions, whether this relation between integrability, namely that the conformal blocks are wave functions of a quantum integrable system, whether that kind of remains to be true for these higher correlation functions. That's what we started to think about in 2020. And let me show you first sort of the challenge, why the answer to this question was not obvious to us. So you remember, of course, this usual statement that the 3-point function of local fields is fixed by conformal symmetry, but it's of local scalar fields that is fixed by conformal symmetry. You can even make one field spinning, but if you make two fields spinning, so you have a 3-point function of one scalar and two spinning fields in 3 or higher dimensions, then it's no longer fixed by conformal symmetry. And the reason for that, so it's a simple fact, not easy to prove. It's very important for the second part of this talk, so that's why I want to give you the argument. Of course, when you have let's say we are in 3 dimensions, the rotation group is SO3, so it has one creation operator, the rotation group, right? It's an isospin creation operator. Then, of course, the conformal group has 3 more creation operators. These are the translations. So if you have a field with spin, you have 4 non-trivial creation operators, right? 1 creates isospin, 3 create sort of translations. If you have a scalar field, you have only 3 creation operators. Now, for instance, if you take a 3-point function of 3 fields, 2 are spinning and 1 is scalar, you have a total number of 4 plus 4 plus 3 creation operators. That's 11. But the conformal group only has 10 generators, so you have only 10 word identities. So you don't have enough word identities to fix the 3-point function. So for 1 scalar, 2 scalar and 1 spinning still works, 10 creation operators, 10 word identities, but for 2 spinning it doesn't. That is not. And that's of course a well-known fact. That's called in conformal field theory literature. You have to introduce tensor structures. So there's something sitting at the vertex, and so there are more coupling constants in some sense. Sorry, more coupling constants, several coupling constants, finite set of coupling constants attached to the vertex. Okay. Now, so again, this is in principle well known. This is also kind of classical. I mean, classical in the sense of 70s conformal group theory. And now, when we want to build the corresponding block, let's say the first time it hits us is we want to build a 5-point conformal block. Okay, so according to what I told you before, what we do is we take this 5-point function and we think of it in terms of an OPE. So we can perform like 2 OPEs here to make 2 spinning fields and then have a 3-point function to evaluate in the end. So corresponding, there's an integral formula here that uses these 3 vertex functions, which are explicitly known, and you integrate over the intermediate quantum numbers. And so this is a concrete integral formula that you can write down. But of course, this integral formula now depends on quantum numbers. So the quantum numbers that appear here are the weights and the spins of the fields, intermediate fields, and this extra quantum number that kind of enumerates possible vertices. Okay. So another thing that I should say, if you have a 5-point function, again, that's a nice exercise that I won't go through here, is if you have a 5-point function in dimension larger than 3 or 3 or larger, then you can build 5 cross ratios. Okay, so you kind of do your counting and 5 cross ratios. And so I pointed out before that these conformal partial waves have to have the same number of variables as they have the same as quantum numbers. And now 4 of these quantum numbers are the weights and spins of the intermediate fields, and 1 quantum number is a new quantum number, okay, that sort of sits at the vertex, has to do with the fact that conformal group does not fix uniquely 3-point functions if they have sufficiently many spins. And so, so now we kind of understood that what we discussed before. I mean, we pointed, I mean, after question before, I pointed out that the Hamiltonians of these Calogero-Sutherland models, they measure weights of spins of intermediate fields, but we don't really know yet what measures sort of the quantum numbers sitting at these vertex. And so, so this is the question that we addressed sort of in 2020 and that we were puzzled about. Can we actually come up with an integrable system which has also Hamiltonians that measure these extra quantum numbers that sit at the vertex? And the answer is yes. And So the basic construction, in fact, is that of Godin integrable models. Now, again, I won't go through this in all detail, but so there's a way to build, a very universal way to build a lot of commuting Hamiltonians. And the way that proceeds is in the standard way for integrability. We first introduce sort of a Lex connection, which is a sort of a family, a matrix valued family of different first order differential operators. So you build, so you pick, let's say we have an endpoint function of local fields, just to be concrete. So then we introduce, we have a spectral parameter omega here, and then we introduce extra n parameters wj. These are complex parameters. And then we write down this particular connection where the TAs here, they are just generators of the conformal Lie algebra, some matrices, concrete matrices realizing the generators of the conformal algebra. And these T alpha j here are these differential operators that we use to characterize a primary field or a defect, the things that we constructed in the second part. So this is a very concrete matrix valued first order differential operator. And then we put it into this, divided by W minus Wj and sum over J. And that way we obtain these matrix elements, basically LA, which are sort of the components of this Lex connection. From these components of the Lex connection, by the standard procedure, you can construct a set of commuting Hamiltonians, which depend, of course, on the choice of these complex parameters, W. Okay, that should be Wj. On the spectral parameter, of course, and so the way you do that is you take sort of your invariance, your killing form and higher invariance of your conformal group, and then you contract a product of these components of the Lex connection with these invariants. You have to add some lower order terms to ensure that everything is sort of, and commutativity is preserved also in the quantum theory, but all this is very well understood. And so you obtain a set of commuting objects, and you can check actually that these commuting objects, and that's also well known, commute, in fact, with the generators of the global conformal symmetry. So if you build the generators of the conformal symmetry, the joint action on all the primary fields, let's say, that are really relevant for the water identities, they will commute with these Hamiltonians. And that means basically these Hamiltonians descend to the space of invariant objects. Okay, so you should think of, again, these are differential operators for functions on the group, and they descend to the first order differential operators, these Hamiltonians, the first order differential operators on this space of invariance, conformal invariance. Okay, that's basically standard construction of Godin models. So you get quantum integrable systems on such a reduced phase space, and you can know, and it's also very well known, that you get enough commuting objects to make this problem integrable. But it's not quite yet, and that's very important, so maybe I should skip, in view of the time that Lina keeps showing me, I should skip my comments. You read the comments and ask me questions about them. I give you time for that. And now let's go. So what's very important is, however, that sort of Godin is, of course, fairly obviously the framework because of these features that produces a lot of intercommuting objects. It descends with the commutes with the group symmetry. It's obviously by Frankel-Rijtiki work. So on Godin, it's obviously sort of the right framework, but it's not quite yet what we need, because the Godin model contained all these parameters omega j, right? These n complex parameters. And in fact, what we want is, of course, we know already that we have a few operators that we really want to construct, right? We want to be able to measure the deltas, the weights, and the spins of the intermediate fields. So among these commuting objects that the Godin construction gives, we should make sure that these operators that measure the deltas and L's, that they are present. And on top of that, we want more to measure also this n quantum number. Okay, so, and it turns out that this actually, so now we can choose sort of any OPE channel, so any way of doing our OPE construction that defines then which deltas and L's we want to measure. And so if we demand that we want the Casimir operators, I mean these operators that measure deltas and L's of the intermediate fields in one particular OPE channel, that they are appear among the Hamiltonians, that actually will force these parameters Wj into some kind of limiting configuration. So typically they're just a bunch of complex numbers, But this will actually force them into a configuration of zeros, ones, and infinity in some sense. Okay? So this is a very important step that actually says that these models that we need here are not Godin, but they're very special limits of Godin, which are much, much simpler than the full-fledged Godin. So here's the formula that goes along with that, and you can read that from the paper. So there's a construction to take now the Godin Hamiltonians, and then using some kind of OPE graph, we have a way of constructing certain indices eta rho, which are attached to the internal edges of the OPE graph, certain polynomials rho, g rho, and f rho, fj. So there's an algorithmic construction of all these quantities, and then you take a limit where you send little epsilon to 0, and you kind of take these Hamiltonians and take some kind of scaled limit. Okay, so the formula is of course hard to digest, but I stress it only because it's very important to understand we're not dealing with Godin, we're dealing with a very special limit of Godin here, and that we're dealing with. So you can show that you can construct these functions. There's now one function. So these are functions which have no complex variables attached to them. There's one function for each internal line of your OPE diagram, or labeled by the internal edges, and of course Q, which is the rank, or the order of the differential operators. And they form a complete set of Hamiltonians. That's something after taking the limit that you have to prove, and that we proved at least for this endpoint function of local fields. And so these limits, so the limit construction, in fact, turned out that some special cases had been discussed in the integrable literature before. It's also known in the context of so-called bending flows, also in the mathematics literature. So this limit construction is not unique to this conformal field theory application, but it's we extended that drastically. So to give you a little bit of the feeling what the limit does, let me look at one example that maybe some of you. So if you take a four-side Godin model, okay, so you take just 4 sides, so it would be relevant the Godin model for the 4-point function of local fields. That's known to be an elliptic BC2 Kalogero-Sutherland model, okay, and or also it's known as Ilmo-Zemtsev model. And this limit that we're taking here basically degenerates that. Degenerates that to a hyperbolic BC2 Kalogero-Sutherland. So you go from elliptic to hyperbolic, in this particular case, from elliptic to hyperbolic by doing the limit. So just to illustrate a little bit the type of simplifications that you get through the limit. So in view of the time, I will maybe not talk about this. So we've looked at some of these Hamiltonians very concretely, in particular for vertex systems that appear in 3- and 4-dimensional conformal field theory. They can be actually identified with known integrable, elliptic integrable systems. But you can ask me about that. So let me come to conclusions and outlook and open problems. So the main message I want you to take away from this talk is that conformal blocks, no matter which conformal blocks you want to talk about, whether you want to insert defects or local operators on the defect or bulk fields, they will be wave functions of some integrable system. Okay? And this integrable system is sort of Godin type, but it's very important. It's not Godin and full-fledged, but it's sort of limits of Godin. So it's hosted in the world of Godin, but it's very special points in this world of Godin. And some examples you have seen would be some kind of Kalogero-Sutherland models. So so that, again, that's sort of the key message. And if you take only one thing away from this talk, then that's what you should take away. Now, let me say that I know, of course, a lot of people in this audience are interested in deformations, so make a quick comment on this. There is actually a very interesting deformation theory for what I've just described, which, I mean, this problem that I described was motivated by representation theory of just standard Lie groups, but of course you can make them quantum. And then from differential equations, you get to difference equations. And in fact, the world becomes much more beautiful. Turns out, it becomes sort of self-dual in many senses. There's a lot of algebraic structure that you can study. That's a beautiful subject in its own, and I'm happy to discuss that more, in particular with people interested in these deformations. This quantum deformation by itself don't seem to have a real applications in conformal field theory. I don't know what this Q parameter would be, except it's a nice parameter even in mathematics that people use to regularize expressions and then take limits in the end. So that's one comment. Another comment that maybe is a bit scattered. I've talked only about kinematics, We have recently been involved in applications to the bootstrap. And so in this case, I should say that, so when you write down the differential operators, you notice I didn't show you many of these differential operators. They look also fairly complicated, right? We can construct them all as differential operators in these cross ratios, but they look fairly complicated. So we usually provide some Mathematica codes that would give the differential operators. But there's one setup where they're actually easy to evaluate, and that is if you start making the distances of points light-like separated. Okay, so it turns out we found some cross ratios when we write the differential operators in these cross ratios. All the coefficients are polynomial, and in these cross ratios it's very easy to take these limits when you make distances light-like. And it turns out that the differential operators often, always simplify drastically when you do this. There's all sorts of decoupling, and in these particular limits, when you make these light-like limits or light cone limits between distances of points, differential operators become so simple that very often you can write down closed solutions for the differential equations. And we have now used that, or are in the process of applying that to do some kind of multi-point analytic bootstrap in conformal field theory. So, so that's one case where, in fact, I could write down the formulas for the differential operators and show you solutions. I haven't talked much about the solutions. I've talked mostly about the differential operators and a little bit hinted at algebraic structure and differential operators. Solution theory, I mentioned briefly that Casimir, what I call Casimir solvable case in the second part. That's something for which the solution theory is completely known, and it will take another lecture to explain, but it's completely worked out. For this vertex system, that's a new type of system that goes beyond this trigonometric Lodger that I described. We have identified one example of this, fairly generic, the one variable vertex system. And we've shown that this is what's called a lemniscatic elliptic Calogia-Moser-Sutherland point. In that case, the solution theory is not known. It's an interesting challenge to find the solutions. But maybe the most interesting challenge I find is now the following. So in some sense, of course, it should be true that if you understand all these subsystems, like these link systems that measure the operators, that measure deltas and L's, and maybe the operators like this lemniscatic elliptical Lodger-Moser-Sutherland Hamiltonian, you should be able to paste together and get really blocks for any number of points. And the more scientific way, I guess, of doing that is in this community of separation of variables. So separation of variables should be a way to really build up these conformal blocks of the wave functions from individual factors that depend only on one variable. Okay, and so I think this is one of the biggest challenges. So the integrable community kind of promises that in some sense there will be a Lego, now kinematical Lego, namely a way to build all these conformal blocks from just little pieces, single variable pieces, right? And you can actually work this out explicitly in the 1D case, because there the separation of variable is very well understood, and you can see that it works out very nicely. In fact, in this case, separated variables are just momentum. So you just go to momentum space, and you can write down all the conformal blocks as a product of hypergeometric functions in momentum space. And that is just the product of hypergeometric functions and not something more complicated. It's again a consequence of this limit that we are taking. So I consider this sort of maybe, from my point of view, maybe the most beautiful challenge in this field. I think there's a promise here that integrability makes, namely that it should be possible to develop such a, let me call it, kinematical Lego. Really, the separation of variables for these Godin limits, I think, is a very interesting problem. That if that was solved, it would ultimately solve the challenge of developing conformal group theory. Okay, thank you.
More questions?
Hi, thanks for the nice talk. So your sort of main statement is that conformal blocks are then wave functions of some limit of Godin integrable system. But do you have any interpretation of, say, some higher structures within the Godin model? For example, if you take some correlation function of local operators in the limit of a Godin model, does this map to something in the CFT side?
In the what?
Does, for example, a form factor of a local operator in the Godin model or a limit of a Godin model map to some object in the CFT?
Form factor in limit of Godin.
I mean, in the sense that Godin model is a spin chain, right? So I can
Right,
take
right.
operators of the Godin model, which are sitting as some individual site. I can take some form factor of this, let's say 2 wave functions, which would be 2 conformal blocks. Does this have any interpretation in the CFT?
I'm not sure, but probably we should talk about this more. But so one thing, so I think I stated what has an interpretation, right? It's the wave functions. So what I didn't maybe stress enough is, of course, that I mean I'm so puzzled with this. So that this construction that I described here, again, has lots of variations depending on what you want to describe in the CFT. So for instance, if you want to have Wilson line operators or things like that, you have to insert different differential operators in this construction. And depending on what your setup is, you get different quantities in Godin. You have different types of representation that you have at these individual sites. So that's sort of the variation that I can see of the problem, with very different quantities would appear. But yeah, I'm not sure it fully addresses your question. I'm happy because you're here. Obviously happy to discuss more.
Hi, sorry, this is just a clarification. You said that no matter what kind of endpoint function you choose, no matter the type of operator that you insert, you can find a differential operator.
We can find a full, complete set of differential operators.
Let me say in another way. It's you state that any correlation function is associated with an Hamiltonian of an integrable system. So this is like a proof. It's
with
valid
a set of Hamiltonians of an integrable system.
Yeah. So this is something that you proved.
I mean, okay, as Terry said.
Yeah, proved enough.
So
yeah,
let's say
That's
if you have the setup where you have a single defect line and a bunch of local operators on the defect line and any number of bulk fields, then I can essentially prove it, I believe.
Yeah, no, that's fine. I mean, it's not
so.
I
mean,
much
eventually, I mean, I was just thinking about the number of local fields that you can insert on the defect you would get in the cyclotonic Godin, and then I'm not quite sure how many I can.
Is there a reason why you do get integrability out of there? Why don't you get a differential operator of a non-integrable type?
It's just, I would say, an observation that you get integrable system, which should get us all excited because it tells us that when we're developing group theory of the conformal group, this community is really in business. We know the technology to do it. Yeah. I don't know what else to say. I mean,
yeah, it's more like giving an interpretation of the fact that you do get integrability. Does it have some meaning?
Yeah.
So, like, for example,
I mean, of course you can. No, I mean, again, one shouldn't look for too much meaning, but of course it follows a little bit these kind of standard laws, right? I mean, if you start with a group, you have many degrees of freedoms, but then you have commuting Casimir operators, and then you have to reduce the number of degrees of freedom through this Hamiltonian reduction to get just as many degrees of freedom left as you have commuting Hamiltonians. So it's a little bit of this type, right? And so fortunately, all these problems that appear in this construction of conformal blocks are of this type. But you have removed sufficiently many degrees of freedom to make the remaining problem sort of integrable.
I think we have to stop here with the questions. Sorry for doing my job not so well. So, okay, let's thank Volker again.